Hello, my name is Piotr Tomaszuk and I am the technical coordinator of Team ARGO. First of all, we extend designing and simulation part of preparations. All of the mechanical parts of the Rover were at first made at the prototypes from foamed PCV, plywood, MDF plates and 3D printed parts. Faculty of Mechanical Engineering also granted us full access to all premises and equipment such as water jet machine, CNC machines, lathes, milling machines, 3D printers or laser cutters. The faculty provided us with our lab where we can work for 24 hours, 7 days a week.
We assumed construction that could overcome 16 degrees inclined slopes and 1 meter high drops with almost vertical walls. To achieve this goal, we designed and developed our made rocker bogie-like suspension system. During test, we manufactured several generations of the prototype of it. Thanks to this, we are able to check almost every configuration between swing arm and the frame. During robotic arm designing stage, we were evaluating different styles and options of the driving joints and used materials. We also decided to develop two manipulators, one main robotic arm and the second specialized to science cage task. The main manipulator is equipped with our design cycloidal drive. Its design is a self-enclosed package capable of supporting the entire weight of the robotic arm and its payload with no additional external bearings required. To improve the maneuverability of the end effector and reduce the time that is necessary for a process of manipulation during competition tasks, we introduce pitch, roll and a jaw-capable wrist at the end of the arm. The mechanism itself consists of metal bevel gears as a differential and two servo mechanisms powering it. Depending on the combination of the servos working, we can move the pitch up and down or roll it. The second manipulator that will be used during science cage task is similar to the mini excavator. We are also going to use our made linear actuators.
In order to provide a much-needed feedback for teleoperator, we create a real-time manipulator visualization. By gathering the information from each joint via the absolute encoders, we are able to visualize the manipulator on the computer screen. The application itself is written in C# language using OpenGL library. It will also work together with inverse kinematics algorithms that provide autonomous movement of the end effector. Moreover, additional tabs designed for each task drastically cut time that the operator spends to change configurations during field task. It also gives us access to view from one of even up to 6 cameras.
Electronics of our rover are divided in the fully modular system. Communication between modules is realized via CAN bus. Each motor has a driver board that controls the speed, position, temperature, load through PID control. Sensors have their own controllers that collect and process the data to the required form. All data is saved in the main controller, which in turn calculates the motion of the robot and sends out control signals. The main controller communicates with a base station through a redundant radio connection, a 433 MHz radio modem and a 2.4 GHz Wi-Fi connection-based network. Right now we achieve even 1400 meters of the operating range in the crowded city.
The autonomous drive system is connected to the main module via LAN network and it is based on NVIDIA Jetson TX2 board. This computer is the perfect choice for image analysis and parallel calculations during autonomous traversal task. The autonomous system uses GPS module, IP cameras and video recognition algorithm, stereo camera technique and 3D LiDAR scan to find obstacles and markers. Right now we are able to precisely locate the markers that are within 5 meters radius and the obstacles in 3 meters radius from the robot.
We plan to examine science site in search for possible life indicators. Collected samples will be examined for possible residues of past and present life forms, with an emphasis on amino acid building blocks of proteins.
See you soon during URC 2018.